let's start working on this assignment. We have the air handling unit with a cooling coil and a heating coil. So that means that we can use this device for winter and summer because we have heating and cooling coils. What's the goal of the air handling unit? We have to provide this space with a good quality air. And so what is the good quality? The indoor conditions. The temperature indoors should be something close to 70 Fahrenheit, 70, 72 is fine. And relative humidity, it's something between, let's say 35 and 55. Relative humidity, it's fine. This is comfort. It depends on the number of people. So if we have 100 people here, that means that we need to multiply the CFM, which is around 20 CFM per person. We have to multiply this times 100 people. So with these indoor conditions and the number of people, indoor conditions are always the same, around 70 and around 50. It can be 70 and 45. It can be 71 and 51, whatever. But it's always around 70 Fahrenheit and around 50% of relative humidity. And then it depends on the number of people. The number of people, it's something that we should know because we as architects, we are designing a building. So we can either ask our client, okay, so you are building, what is this? School. Imagine that those are classrooms. Okay, so what is the occupancy of those classrooms? Every classroom, 30 people maximum. Okay, so now you have data. So these are data. We should know this beforehand, before designing the building or even designing the mechanical system of the building. We should know at least the indoor conditions, the outdoor conditions in winter and summer, and we should know the occupancy, the number of people that are occupying that are living in that building. And then what we have to do, we need to provide this with fresh air, a healthy air, but at these conditions. Outdoors, if we are in winter, it's cold, we have 32 Fahrenheit and 70% relative humidity. If it's summer, it's hot, it's 90 Fahrenheit, and it's dry. Usually summer, the outdoor air it's dry. So let's say 30. So those are not comfort conditions. This temperature is too low and this relative humidity is too high. And in summer, it's the other way around. The temperature is too high and the relative humidity is too low. Okay, so that's why we need this air handling unit. If we are in winter, we need to use the heating coil. If we are in summer, we have to use the cooling coil. And this is what we have to calculate. The ventilation airflow for 100 people and the indoor and outdoor enthalpy. And then the heating power in BTU hours. And finally, the energy. So this energy, the daily energy, is this is what we have in the energy bill. Okay, so in Eversource, it doesn't inform us about the number of people, about the enthalpy, about the heat, not even about the heating power. They informed us about the daily or the monthly energy that we are consuming. Okay, so but we are the designers, we are the building designers. We need to know all the process, but our client will receive only this information, will receive the daily energy, and they won't understand anything because they will understand the dollars, the money. This is what they understand, the clients. Okay, so that's it. Okay, so now first, what is the airflow? The airflow, it's always 20 CFM times CFM, sorry, per person times 100 people. Okay, so total it's 2000 CFM. What are the indoor conditions? The indoor conditions are here 72 Fahrenheit, and 50% relative humidity. And outdoor conditions, we will start with winter. In winter, we have 32 Fahrenheit and 70% relative humidity. Okay. So what is the thermal load in winter? So the thermal load in winter, here, we have to multiply the airflow, it's 2000, and we are going to work with units because working without units, it's confusing. So we will work with units. So this is a cubic feet per minute, so it's divided by minute. But we have to work with BTU hours. Okay, so at the end, the final units, it has to be something in BTU over hour. So we're not working with minutes. So now we have to multiply this times 60 minutes divided by hour. Okay. So now we have cubic feet divided by hour. Now we have to multiply this times the enthalpy. Okay, so we have to indoor, we need HI, we need the enthalpy indoors, and outdoors in winter we need HE, we need the enthalpy outdoors in winter. Where can we find this? We can find this in that amazing free psychrometric chart. Okay, so this is in first, we have to go to settings, English units, reset all inputs, submit. Okay, and now here we have to click here, input data for air properties, and we have to calculate the enthalpies indoors and outdoors. So the indoor conditions, it's 72, and relative humidity 50. We submit, and the enthalpy it's 26.46. Okay, so the indoor enthalpy is not this one. 26.46 units. BTU per pound. Okay, so this is BTU per pound. So let's write it down. BTU per pound. Where is it? Pound. What's the enthalpy outdoors? Okay, so we have to go here. The temperature outdoors is 32. The relative humidity is 70. We submit it again. And the outdoor enthalpy is 10.54. There you go. So this is 10.54 BTU per pound. Okay, so in this formula, this is 26.46 minus 10.54. And the units here are BTU per pound. Okay, and now we have to divide this by the specific volume. And well, if we go over the specific volume here, in this case, the specific volume is 2.5. Indoors, it was 13.5. It is 12.5, sorry. And the other one was 13.5. I don't know, it's something between 12.5 and 13.5. We can say 13, and that's good. But everything is correct. Okay, so if you write down here to 12.5, that's fine. If it's 13, that's fine, because we are not talking about decimals. We're talking about terms. So the units are, it's not even a decimal. So we're not worried about units, because BTUs are, they are not the units that we're going to use. Then we're going to divide this by 100,000. Okay, so 13 or 12.5, it's fine. And units are feet, cubic feet divided by pounds. Okay, so what is the, make it smaller. What is the total value here? So this is 146,953. BTU per hour. I'm going to make it smaller. There you go. So some of you have, Melissa, I think you have this, you have 146,000 kind of. Am I wrong? Okay. So it has to be something like that. It can be 130,000 or 150. I don't mind, because, but it's something close to 100 and something, 150,000 BTU hours. Okay, what is the energy now? And this is the scary moment, because if we are talking about energy, it's 146,953 BTU hour times, I think it was like the system operated for 10 hours in winter and 12 hours in summer. Okay, so we have to multiply this by 10. 10 watt hours. So that equals 1,469,530 BTU. So you were scary about what? 1.5 million BTUs. Yeah, 1.5 million. So that's why if you receive that electricity bill, 1.5 million, and this is one day, because this is 10 hours, it's a day. So if we multiply this times 30 days, so there will be like, I don't know, 30 million, 40 million BTUs. We are crazy. This is the end of the world. No, it's not. Because now, if we want to turn this into therms, we know that one therm is 100,000 BTU. So this is 14 therms. That sounds less scary. 14 therms, okay. It's not that bad. If we look at the electricity bill that we saw at the beginning, yeah, so it's the total monthly consumption. It's like 100 therms, and on a daily basis, we are consuming here like 14 therms. Yeah, so it's the same order of magnitude. So the magnitude is important. It can be 14, it can be 12, it can be 15. I don't mind. But if it's 1,000 therms, what, 1,000? No, it has to be 14. Okay, so if you don't have we are not looking even at the decimal here, because look at this. Here, I told you that it can be 146,000, or it can be 130,000 or 150,000. I don't mind, because this will be 13 therms, 14 therms, 15 therms. Okay, so even that number is not important. But if it's 100,000, it has to be close to or between 100 and 200,000. Okay, so this sense of figures, it's very important, because when you have calculated thousands of these kind of exercises, then you don't have to calculate anything. Okay, so what's the size of the building? 2,000 square feet. Okay, how many people? 100 people. Okay, so it's gonna be around 20 therms. It might be 20 therms or 16 or 22, but it should be around 20 therms. And this is how professionals work. Yeah, but we need experience, so we need first we need to get older, which is not and finally we need to work on that field for years, and we need to be around people that know what they are doing. So with these three aspects, with time, a lot of experience, and good people around us, we don't have to calculate anything. But first, yeah, so we have to check this. Okay, so in summer, the summer conditions were 95 Fahrenheit and 30%. So what is the enthalpy in summer? We have to go to the chart, summer conditions 95, relative humidity 30, submit. Okay, so in summer the enthalpy is 34.5. So we go back here. In summer the enthalpy is 34.5 units BTU per pound. And then we have to do this again. The airflow, it's the same, so it's 2000. So now this is winter. Sorry, now this is summer. The airflow is the same. It's around 2000. 60. We have to turn minutes into hours. And here, the indoor. It's outdoor minus indoor. Okay, so this should be 34.5 minus this, and this can be 13. What is the, well, this is 14. Okay, the other one was 13.5. This is 14. Well, probably in summer we have to take something in the middle between 13.5 and 14, so we can say 13.7 again. And now this is 2000 times 60 times divided by 13.7. Okay, so this is around 70,000 around. Okay, I'm not going to it's around 70,000. And the energy, it's 70,000 times 12 hours, because in summer it was 12 hours. So that would be times 12, around 841,000 around. So this is 8 terms. Okay, so it can be 8, it can be 8.4 terms, 8.2, around 8. Any questions about this?
No. Fernando, why was it 13.7 instead of 13?
This 30.7, this one. 13.7, you mean this this figure here?
Yeah.
Okay. Because in this chart, this is the outdoor enthalpy. No, specific volume. This is the specific volume. So this is around, it's 14.2. But if we calculated the indoors was 72 and 50. So we submit. Now the specific volume, it's 13.5. So I took something in the middle between 13.5 and 14. So 13.7. You know what I mean?
Okay, thank you. And then also, can you just show me one more time how to go into settings and change it to Fahrenheit instead of Celsius?
Okay, so let's close this. So you open, so by default, you are in Celsius, and then you have to go to setting. You have to select English. And here, this is the most important thing. You have to reset all inputs based on units. And then submit. And there you go. If you don't do this, I mean, if you close it, you're here. And you just go to settings and change this and submit. Yeah, something terrible happens, okay? So you need to reset the inputs and then submit it again. And then you have this nice chart. Is it clear now?
Yep, thank you.
Okay, any questions about this? You all have to submit it. So now you know the answers. You know that the summer is around 14, in winter, sorry, it's around 14 terms. And in summer, it's around 8 terms. So it has to be something like that. So go ahead and just, but I want you to go step by step. So I don't want just the final number and that's it. So show me all the steps, show me what I have done here, okay? The airflow, then the indoor conditions with the indoor enthalpy, the outdoor conditions, the summer and winter enthalpy, and then this formula here, because if there's something wrong, I can understand where the mistake is. If you just give me the final answer, I don't know if it's, well, I can know if it's right or wrong, but I don't know where the mistake is, or if there's an issue in the process, I can't find it. So get used to writing down everything, even the formulas, and especially units. Units are very important, okay? Because so after every single figure, make sure that you write units, because it will, if you make a mistake, you can understand where the mistake is, and but especially it'll help me understand what you have done, okay? Because if I see only 2060, 34 minus 26, but if I see the units, I see if something's wrong. Okay, so what are we going to do now? We are going to show another aspect of air handling units. The first assignment was something very simple. Okay, so we used these schematics. I'm going to copy this. Here. Okay, so this is what we have done so far. The most simple air handling unit with a heating coil, a cooling coil, and we have an air inlet and an air outlet, and that's it. Now we are going to circulate this indoor air. Instead of, because with this indoor air, the problem is that eventually this air okay, so this is fresh air, conditions are pretty good, but then those people are moving and sweating and all that. So eventually we will, so that air will take all the particles and the water, so it will be unhealthy. Okay, so I'll change the color of this. Okay, so eventually this air, it would be unhealthy, and finally we have to get rid of it. Okay, so we need to get rid of this air. Okay, so this is what happens. We have fresh air, then the air becomes unhealthy, and then we have to get rid of it. But getting rid of it, that means that we are losing a lot of energy, because this air we have here, it has a lot of energy. It has useful energy because the thermal conditions are good. Okay, so those are comfort conditions. The problem is that there are particles that we have to get rid of. So instead of have another grill here and let the air go out, we're going to recirculate this air. So we are going to take this air, so there will be a duct, and we will circulate this air to the air handling unit again. So this is what we're going to see now. So I have recorded myself drawing this, so I will, so the most important thing, as always, is the people. We have to make people happy. But people, the happier the people, the more they move and the more they sweat. Okay? And now we need an air handling unit to provide people with comfort. And comfort is good temperature and good relative humidity. So we have to get rid of this relative humidity, all these particles that we are expelling when we are breathing or we are sweating. So the first thing is that we need the envelope. We need the building envelope. So we have walls, floors, roofs, windows. And the most important thing now is the thermal insulation. Okay, so this is our building design, but now we have to use thermal insulation to protect that building from the outdoor conditions in winter and summer. And now this is the thermal insulation. There you go. Okay, so this symbol is always for thermal insulation, and we need an envelope with thermal insulating materials. In the floor, usually the floor is we have less thermal insulation, or the thickness of thermal insulation in floors is not as much as the thickness of thermal insulation in walls and roofs, because we all know that heat tends to go up. Okay, so we have to protect the roof against the thermal losses, and floor is not as relevant, but I like the idea of having thermal insulation also in the floor. Okay. So after that, when we are done with the thermal insulation, then we need to understand that we have windows. Okay, so windows are weaknesses in our walls or in the thermal envelope of the building, because we have thermal insulation all around the building, but we have windows. We need windows because if we have nice views, or and we need natural light. Okay, so we need windows, but we have to be careful with windows because they are weaknesses in the thermal insulation of the envelope. And now we're going to add something else. We are going to add the basement. We're going to add a basement because usually all these mechanical systems are on the basement. Okay, so we need a basement with the mechanical systems on it, with boilers or chillers or whatever. So there's a basement there. And on that basement, we are going to place the heating system. So we have a boiler. Let's say that it's a gas boiler. So this is a heating system. And then we have a chiller. We need something to cool down the air. Okay. So this is a chiller, which is something blue, something like that. Yeah. And now we need a boiler, we need a chiller. Those are the energy production systems. And now we need the air handling unit. The air handling unit usually is on the top of a building. Why? Because it has to be in contact with outdoor air. Okay, so we're going to place the air handling unit on the top of the building. So the first thing is a fan. We need to move that air. So we need a fan. Okay, so because the air is moving and we have to control the airflow. And then we are going to need coils. We need a heating coil. And we need a cooling coil. This is heating and this is the cooling coil. Okay, so this is what we did last time. We had the air handling unit with a heating coil and a cooling coil. But now we are going to add something different, the heat recovery. Okay, so there is another box in our air handling unit, which is the heat recovery. Something wrong there. Okay, so usually a heat recovery, it's something like that. Okay, so it's like a square, like a rotated square within another square. So all this is the air handling unit. So it's a huge box, and this is on the roof of the building. So this is the air handling unit. What else? So now we need we need air inside the building. Okay, so we have the building, we have all systems, we have the heating system, the cooling system, and the air handling unit for heating, cooling, and ventilation. So this is all we would need in a system. We don't have these kind of things in single-family houses because now we are talking about commercial buildings. So we need two openings because we need ducts. Okay, so there's a duct that goes from the air handling unit to the building. Okay, so there's a duct here, and we have a diffuser or a grill, something that distributes the air. And now, instead of getting rid of this air, we are going to recirculate this air to the air handling unit again, and that's why we have this heat recovery. Okay, so we have this. We have another grill somewhere, and we will get rid of this exhaust air, but through the heat recovery. And this is what we are going to do now. So now we will draw the airflow. Okay, so this is the air supply. So we are supplying air at comfort conditions. through those grills. Then this air will go through the people, so people will breathe this air, but at the same time, they are filling that air with moisture, particles, pollutants, and now we are going to recirculate this air through this grill to the heat recovery device. So it goes through the heat recovery. Okay, so this is the air supply, and the other one is the air return. Okay, so in all these systems, when we are working with air handling units, we always have a supply and we always have a return. If you are in the TDS center, I'm sure that in every single classroom, you will find supply grills or supply ducts, and you will find a return ducts. So this return duct goes through the heat recovery, and we get rid of that air. But part of the energy that this return air has, okay, we are heating up, or we are warming up the outdoor air that goes through the heat recovery, okay? And now it goes through the heating coil, and then we warm up that air at the required indoor temperature. Okay, so that device there is what is new. So this is the heat recovery. There you go. So outdoor conditions, it's 32 Fahrenheit, 70% the relative humidity. Those are outdoor conditions. And indoor conditions are 72 Fahrenheit and 50% relative humidity. Okay, so with the previous schematics, we just we didn't recirculate the air. We didn't have this return grill, and we didn't have the heat recovery. We will evaluate the savings that we can have with this system. Then to complete the system, we need water. So from the heater, from the boiler, from the gas boiler or whatever, we have a water pipe that goes to the heating coil, and then we have the return. Okay, so when we have a dashed line, that means that it's returning. So the first line is the supply, where the circulating pump is, and then we have the dashed line with the return. And for the cooling coil, we will have the same, but from the chiller. So there's another water pump pumping the water up. So it goes to the cooling coil, and then we have another dashed line, and the dashed line ends up in the chiller again. Okay. So I think this is it. Oh, no, it's not, because we have a chimney. Okay, so if this is a gas boiler, the boiler is burning gas, and we have to get rid of this exhaust air, and we cannot mix this air from the boiler with the air handling unit. So that's another duct, and it's not connected to that air handling unit, that the chimney. Okay, so this is it. Here we have everything we need. We have the air handling unit. The air handling unit has a fan to move the air, because we need the airflow. Then we need a heating coil. Then we need a cooling coil and a heat recovery. we have to supply this air at these conditions, at comfort conditions, but this air, it's getting wet with moisture, particles, whatever, and now we have to get rid of it. But the temperature of this air is 72 Fahrenheit. And outdoors, we have 32 Fahrenheit. So through this heat recovery, we don't mix the airs, we just transfer energy, okay? So in this device, in the heat recovery, we are not mixing, so the excess of moisture and the bacteria or viruses or everything that we might have in this air in contact with people is not mixed here, so it's not recirculated. But the energy, part of the energy that this air has, it's taken here. So what is I think if we work with temperatures, we can understand this better. So the air temperature here is 32 Fahrenheit. Okay, the air here is 32 Fahrenheit. It's just winter air and that's it. After the heat recovery, here in the return, the temperature, the air temperature is 72 Fahrenheit. And this is 72 Fahrenheit. Okay, this is 32, this is 72. Here we have this heat recovery, and probably the temperature here after the heat recovery, it's not 72, it's not 32, so let's say it's around 50 Fahrenheit. Okay, so the temperature after the heat recovery, we warm up this air from 32 to 50. And then we need to heat up this air to 72. Okay, so those are the savings because this is for free. This first warming up is for free because we are just recirculating the air. We are not adding any energy here because this is a system. It's complicated, so we are not designing heat recoveries, but we have to use them. Depending on the efficiency of this heat recovery, this temperature would be higher or lower. But the important thing is that we, for this heating coil, this is the actual energy we're using with our heater or with our boiler. We are not heating up air from 32 to 72. We are heating up air from 50 to 72. So those are the savings. In that schematics, it wasn't like this. So in this, okay, so this temperature was 32 and that temperature was 72. So all this heating coil was heating up all this air, the airflow from this temperature to that temperature. Here we have the heat recovery. So the heat recovery helps us increase the air temperature, and those are the energy savings. Okay. So this is the theory. And this is difficult for us, for architects, because that means that we need supply ducts and we need return ducts. With these schematics, we only need supply ducts. We don't have a return. We just open this and we open, we have a grill here. We don't need a duct. We just have an opening in that wall and we get rid of that exhaust air. But here, we are not doing this. We are doing something more complicated. We are recirculating the air to take some of the energy that this air has. Okay, so we are complicating things from the architectural point of view, but we are saving energy. And well, this is what why we or what we get paid for. We have to complicate things from the design point of view, but at the same time, we need to save energy. This is our goal. So these calculations are slightly more difficult because we are not just heating up air, we are just mixing that air. So we need to understand the energy that we are taking for free from that recirculating the air. Can we do that with by hand? We can. Can we do this using the psychrometric chart? We can. This is what we're going to do now. And the most important thing is that we can do this with Revit. Okay, so today we're going to use the psychrometric chart to calculate this. And probably on Thursday, we will start using Revit, because with Revit, we can include air handling units, we can include boilers, chillers, and we can include the air ducts, then we can include the water pipes. Okay, so we can do this with our actual building with Revit, and we have modeled the building with Revit, and then we can start placing all these devices, and then we can connect the air handling unit to this, or we can connect this cooling coil to the chiller. Okay, so there are a lot of options in Revit. But first, today we're going to use this. So how can we use this? Okay, first we are going to solve the problem that we have solved at the beginning of the class using this psychrometric chart to see if it works. So you see that we have different tabs here. We're going to use now the process. Yeah. Okay, so we have the basic, and here we have the process. The first thing, I don't know, at least here, there are a lot of options. This is 1, 2, 3, up to 10, with different dry bulb temperature and relative humidity conditions. We always can change this, but we are always going to work with the dry bulb temperature and relative humidity. So the first thing I would do is to delete all these. Okay, so you can click here and we can delete all the previous conditions. So we are with a clean slate, okay? And we can start with the problem. So okay, we don't have any condition here, any previous condition here. So the first thing is you can click the plus sign here, and this is number 1. So number 1 can be the outdoor conditions. So our outdoor conditions in summer were 32, and the relative humidity 70. Okay, so outdoor, or number 1, it's 32 Fahrenheit, 30%. Now we click plus again. And then number 2 is 72. And relative humidity is 50. Okay, so this is what we have done before. And now you see that we have point A1 and point B2. State changes from point A to point B. Okay, so here we have airflow, but the units are pounds per hour. What the hell is this? Because our airflow was in cubic feet per minute, but now we have to use pounds per hour. Well, that's the beauty of units. We are talking about the same magnitudes, but with different units. And if we make a mistake in the units, everything would be a mess. So we have to be careful with the units. This is the only concern that we need here. And we have to turn this, because now the inputs here, it's in pounds per hour. I can't change that, okay? So I need to work with pounds per hour. How can we work with this? Okay, so now in this PowerPoint, we need to copy all these calculations here. And the airflow, well, let's this is indoor and outdoor. Yep. So we are going to work with winter, only with winter. Okay. So this is indoor and outdoor. So we have CFM. CFM is 2,000 cubic feet per minute. We had to multiply this times 60 minutes per hour. So this is cubic feet per hour, because we cancel minutes and minutes. But what are the units in the psychrometric chart? The units in the psychrometric chart are pounds per hour. Okay, so we have hour, we have pounds. So what's the relationship between pounds and cubic feet? Again, the specific volume. So we have to divide this between the specific volume. And what is the specific volume? If you remember, we used 13 cubic feet per pound. Okay, so now if we have this formula, this is the airflow, but we need airflow, and the units are pounds per hour. So the airflow in pounds per hour is 2,000 times 60 divided by 13. And this is, if I'm not wrong, it's 9,230 pounds per hour. Okay, so this is the airflow. We made the calculations with 2,000 before by hand, but now we are using the chart, and the chart, we need pounds per hour. So again, we have all data here. So this is the CFM, cubic feet per minute. We need hours and we need pounds. So by using this specific volume, we can have here pounds per hour. So now we go to the chart again. And here I type in the airflow, I type 9,230 pounds per hour. And that's it. So first, I need the outdoor conditions. Second, I need the indoor conditions. Third, I need the airflow, but the airflow in pounds per hour. Why isn't this guy using cubic feet per minute? I don't know, but he's using pounds per hour. Okay, so we have to convert units, and now we submit. Oh, we have to click here, compute and draw processing line, submit again. There you go. Okay, so here we see the lines connecting 2 points. This is outdoor, this is 32 and 70%, and this is 72 and 50%. So there's a line connecting these 2 dots. Okay, so on this psychrometric chart means that here we have something, we have a device that converts, or that goes from this point to that point. What is that device? The air handling unit with a heating coil. And what do we have here? Here we have the heating load. You see that the heating load here is 2,448 BTUs per minute. Why don't we have BTU per hour? Well, I don't know. We have to ask Mr. Interactive Psychrometric Chart, because those are the units that he's using. But again, I only have to turn minutes to hours. It's a piece of cake. So this is 2,400, let's say 2,450. Okay, so this is the Q, the heating load, is 2,450, and units are BTU per minute. And now we have to multiply times 60 minutes divided by hour. So if you multiply 2,450 times 60, the result is 147, around 147,000 BTU per hour. So what's the difference? The result with this is around 147, and the result with this, it was, well, I have deleted that because this is the winter, but it was 146,000, sorry. Okay, so it's almost the same. So here it's 147, and the other one was 146. But it's the same. So by using the chart, we only have to convert units. The problem is that the units that the chart is using, they are imperial units, but well, here we have pounds per hour instead of cubic feet per minute, and here we have the heating load. It's BTU per minute instead of BTU per hour, but it's the same. Okay. So I think what do we have to do now? We have to become familiar with units, and we have to do this a couple of times more, but now using the psychrometric chart and using your own calculations by hand. Okay, so we have to see if the final result it's the same. And I told you it can be 1.4, 1.3, or 1.5. I don't mind. But it has to be around the same value. Okay, so I'm going to repeat this once more. So first, open the psychrometric chart. I'll start the settings. So we need English, reset all inputs, submit, and now we have a nice chart in imperial units. Now we have to go to process. In process, I can delete all these things I have here. Okay, so I need to start from scratch. So I select point one. Point one is the outdoor condition. It's 32 Fahrenheit and relative humidity 70%. Second point, it's indoor conditions, 72 Fahrenheit, 50%. So we go from A, which is point number 1, to B, which is point number 2. If we have only 2 points, that's easier. And now we need the airflow. Okay, so if we go to the airflow, we need to convert CFM into pounds per hour. So this is 9,230. So this is 9,230. We just need to compute and draw processing line. We click here, submit, and there you go. So you can check whether this line starts in 32 and 70 and it ends in 72 and 50. So yeah, so it's correct. And now we only have to check the heating load. Why heating load? Because we are moving in this direction. Okay, so if we are moving in this direction, we are heating up the air because this is a temperature. So we are going from 30 something to 70 something. So that's why we have heating load. So the heating load is 2,448. Let's say to 2,450. And now I have to turn this. This is 2,450 BTU per minute times 60 minutes per hour, and it's around 146,000 BTU per hour. Okay, what if we do this with the winter conditions? If we go to the winter conditions, then our point 1 is not this. The point 1 is the indoor. So we go from 72 and 50, and our point 2 is the outdoor conditions, the summer outdoor conditions. So it's the 95 and 30. Okay, so those are the summer conditions. The beginning, it's indoor, 72 and 50. The final, no, I'm going to do the other way around. So the first one would be 95 and 30. And the second point would be 72 and 50. What about the dry air flow? It's the same. So we don't change the dry air flow because it's the same. We compute, submit. Okay, so we go from this point now to that point. And look at this, we don't have a heating load, it's 0. We have a cooling load. Okay, so for the cooling load, now it's 1,240 around. So it's cooling load is 1,240. These are BTU per minute times 60 minutes per hour. So this is 1,240 times 60. It's 74,400 BTU hour. So this is 74, and what was the original one? Around 70. Okay, so it makes sense. Do you see that we have different ways to get to the same result? Okay, so we can use the old-fashioned psychrometric chart. Okay, so if you are against new technologies and you don't like internet and you hate Bill Gates and all that stuff, you can always copy an old-fashioned psychrometric chart. There are plenty of them. Okay, so you can always use this chart, and okay, 70 and 50%, and then you go in different directions and you take the parameters, the enthalpy, the dew point, everything like that. Okay, so we can do this totally by hand. If we use this, we can go to the basic tab, and on the basic tab, one by one, I can find out the enthalpy of the interior conditions and the enthalpy of exterior conditions, and then I can make all these calculations by hand. Or you can go to process, and then we go from point 1 to point 2. We have to change the airflow, and then we have the heating or the cooling load. Is that all? No, not at all. Because we can, this tool is amazing. And look at this, we have the basic, we have the process, and we have cycle 1. Okay, so using cycle 1, look at this. So we have the room, we have the air handling unit, and we can return this air to the heat recovery. Okay, so with this chart, we can solve complicated problems because yes, mixing up different airflows and heat recoveries, and that's doing this by hand, it's quite complicated. So by understanding what we are doing, we can use this tool to solve these complicated thermodynamic problems in air handling units. So this is incredible. I didn't have this when I was a student. And then we have cycle 2. In cycle 2, it's even more complicated because we have a primary return and a secondary return. We're not going to use this, but next Wednesday, but next Wednesday, no, on Thursday, so this coming Thursday, day after tomorrow, we are going to use this cycle 1 option to calculate what we have explained today. Okay, so today we have been explaining this, the idea of supply and return and the heat recovery. So on Thursday, we are going to use the psychrometric chart to calculate this option and to find the energy savings that we can have here. So that's it. That simple tool that is for free. Most of the best things in life are always for free, kind of. But this is for free, and it's a very good tool. So we can spend thousands of dollars in complicated software to calculate these kind of things. But this tool is amazing, and it's for free. So let's make the most of it.